The speaker is Meng-Chwan, and he will tell us about from little strings to M5-branes and number theory via a quasi-topological sigma model on loop group. Please.
All right. Thanks, Kentaro, for the nice introduction. And thank you again to all the organizers who invited me to speak at this very nice workshop. So as what Kentaro mentioned, I'm going to talk about this title, From Little Strings to M5-branes and Number Theory via quasi-topological sigma model loop group. Well, it's a mouthful, but not to worry. The ideas are pretty straightforward, and I'm pretty sure you understand most of what I'm saying. Okay. Oops.
I didn't catch that.
Oh, sorry. Okay. So the outline of the talk will be as follows. First, I'll give an introduction and motivation of why we want to do this and what is this work about. And then I will give a summary of results. So if you will, this is like a gong show. In some sense, an elevator pitch, I guess, this concept of elevator pitch, where I'll summarize the results. So just in case you have to leave the talk halfway, or if you didn't catch some of the details, you would know what you should be looking out for. Okay, so I regard this part as very important. So if you just pay attention to this, you pretty much get the main ideas of this work, and the rest are just details. And then I'll go on to the main body of the talk, where I will explain the details and the computations from which we get our results. Okay, and then I will conclude the talk about what we have derived, and then we'll talk about some interesting future directions. Okay. So in this talk, we will discuss, okay, let me just minimize this. Okay, in this talk, we will discuss a quasi-topological twist of a 2D n equals to 2 nonlinear sigma model on worldsheet CP1 with target space, the base loop group omega SUK. All right, so what do we mean by a quasi-topological twist? Most of us are familiar with the topological twist of the 2D model, which was first studied by Witten in the late 80s in 1988. So in the topological twist of that theory, the operator observables are independent of the position on the worldsheet. Okay, so if we have a quasi-topological twist, that's slightly different. We have a Z dependence on the worldsheet, but no Z bar dependence on the worldsheet. So there is a holomorphic dependence on the worldsheet of the operator observables. And this also means that we can take partial derivatives in Z of the operator observables. And what this means physically is that, the operators which have no partial derivatives in Z, these are considered like the ground states of the sigma model, just like in the topological field theory, topological sigma model. But the ones with the partial derivatives, which have conformal dimension greater than holomorphic conformal dimension greater than 0, we can interpret those states as left-excited states. So essentially, by studying a quasi-topological twist of the theory, we can study the topological sector, which we know so very well, and we can also study the left-excited sector of the sigma model, right? These things are described mathematically by what we call chiral differential operators. I will talk more about it later on. In the topological case, they are described by Durand cohomology classes in the A model, and Dobol cohomology classes in the B model. This is all very well known, and these two models, the A and the B, are linked by mirror symmetry. That's in the topological case. There is some kind of mirror symmetry for the quasi-topological case too, but we won't talk about that today. So the purpose of us studying this quasi-topological twist is that we want to use it to study the following. Okay, so the motivations for studying this model are the following. We want to describe the ground and half-excited states of the 6D AK-1, the A type n equals to 2, 0 little string theory. Okay, as we will explain later on, the topological sector of this sigma model can be used to describe the ground states, and the half-excited states of the sigma model can be used to describe the half-excited states of the little string theory. Okay, we will go into those details in a while. So, and the other motivation is to also obtain a physical derivation, which in some sense, a physical derivation and generalization of a math relation by Braverman and Fickelberg, which defines the geometric Langlands correspondence for surfaces. Okay, so this is different from the usual Langlands correspondence that people have been talking about for complex curves. This is for surfaces, meaning that it involves 4 manifolds. Okay, it involves instantons on 4 manifolds on one side, involves affine algebras on the other side. Okay, and we would be able to again use this model and in a theorem by a tier to derive this Braverman-Finkelberg result for geometric lengths for surfaces and also generalize it. So we would regard this physical derivation of a math result by Braverman and Finkelberg as some kind of mathematical verification or corroboration of what we are doing so far. Okay, and then of course there is this connection between the little string theory, the states of the little string theory, and that of the BPS sector of the M5-brane world volume theory. And so in our ability to describe the states here, we would also be able to sort of elucidate, some properties of the half and quarter BPS sectors of the M5-brane world volume theory. Okay, so this is the introduction and the motivation of what we're doing, why we want to do this. Okay, so this talk is based on a paper that I wrote with Mir Ashwin Kumar and some of my students. It's kind of long, so I tried to compress it all into one page. So it's a kind of similar title, but it appeared in 2018. But it was based on earlier insights of works that I did over the years. So this is where I first studied the quasi-topological sigma model and its relationship to this, the technology of chiral differential operators in math. And the Braverman-Finkelberg relation of geometric lengths for surfaces was physically sort of elucidated in this paper here. So some insights were also been from this paper. And in this paper by Digraph, the mathematics of 5-branes, it summarizes, sort of a few years or sort of a time period of work, which relates the little string theory to the BPS sectors of the M5-brane. And we will also be able to use some insights from this work to get our results. Okay, so now to give you a concrete summary of the expressions that we'll be getting. So first, in the quasi-topological sigma model with target the base loop group of SUK, I'll explain what that means. There is a scalar supercharge, okay, Q plus bar, which generated supersymmetry, survives on a CP1 row sheet. It's scalar, so it's independent of the genus. So whereby in the Q plus cohomology, so we're looking at operators which are annihilated by this supercharge, but are themselves not written as a Q exact, a commutator of the supercharge. Okay, we have the following currents that generate the following toroidal algebra of SUK. Okay, so we actually get this result here, very nice result here. And if you look at this expression, it's the usual affine algebra that we know with one extra index. Okay, so that's why it's called a toroidal algebra. So the affine algebra is in some sense a loop version of the Lie algebra. So you have the Lie algebra index, and then when it becomes affine, you have an extra index here, M1, which is associated with the loop for an affine algebra. If it's a toroidal algebra, you have a second loop here. So you can see that there's an N1 here. So there are two of these indices here, and this M and N, they span all integers, okay, from negative to positive. Okay, and A and B are just the Lie algebra indices of SUK in our case. Generally, you have the Lie algebra index of any group G. Okay, so, and then we get this. So in the quasi-topological sigma model with this target, we actually get in the Q cohomology operators whose OPEs actually give us this toroidal algebra of SUK. And then if you just specialize down to the topological sector of the sigma model, meaning if you look at the operators which with conformal dimension 0, and therefore the topological sector, we will actually get an affine algebra. Okay, so how you can understand this is actually the following. So this here, this M here, this index here actually is the eigenvalue for that conformal dimension operator that we are looking at. Okay, so and then when you set it to 0, you actually get this affine algebra here. All right. So in some sense, you could think of it as like, a sigma model, which in the topological sector, you could shrink one of the dimensions down such that the S1 fibration of the CP1 disappears, and then you're left with just one loop. Okay, the target space itself, the loop group itself also has loops that are mapped to the group G. So we have two loops, as you can see. So in this case, where you do not collapse the row sheet into just a line, then you would have two loops, one coming from the loop of the row sheet and the other one coming from the loop of the target space. Okay, so if you collapse one of them, and then in the topological sector, and then you would get this expression without the M index. Okay, so this is just the physical intuition of how we got the results. Okay, so then we go on to use a theorem by Atiyah, a very, very nice theorem by Atiyah, which relates instantons on R4 with holomorphic maps of CP1 into omega SUK. Okay, this is a very nice theorem by Atiyah, and how that theorem was being proved is roughly, you have instantons which are topological configurations on R4. You compactify two directions on R4, reduce the instanton equations, and they ought to be the same. And then that's where you get equations which show that there is a map between the compactified S2 in two directions onto this base loop group. Okay, so that's a purely mathematical construction. So via theorem by Atiyah, okay, we can say the following: the left excited states, okay, in the discrete light cone quantization of the 6D A n equals 2, 0 little string theory of R5, 1 can be related to the Q cohomology of the quasi-topological sigma model. Okay, so I will explain why. Essentially, just to jump ahead in case people get lost afterwards, the discrete light cone quantization of this 6D little string theory has been shown to be captured by another sigma model, a 4-4 sigma model, on the moduli space of instantons on R4. Okay, and so Atiyah's theorem allows us to relate this moduli space of instantons on R4 and its observables on it, okay, with the observables on the moduli space of holomorphic maps from CP1 on the omega SUK. And that's how we are able to use the sigma model on the loop group, which is a 2-2 sigma model, to actually say something about the DLCQ spectrum of this little string theory on R5, 1. All right, and so the left excited states of the little string theory would be related to the left excited states of the quasi-topological sigma model, the 2-2 one. Okay, and then we have this conclusion from there that the left excited spectrum of the little string theory will be, captured by modules of the toroidal algebra. Okay, and that's because in the Q cohomology, in the excited spectrum, we have this toroidal algebra here. And then likewise, the ground states of the little string theory can also be related to the topological subsector of the model, and that will be related to the modules of SUK. And that's because here you can see that in the topological sector, we have an SUK affine algebra. Okay, now let's go on. So then, via the expression for the ground states, meaning looking at the ground states here, okay, we would be able to derive this relation, or to come to this relation. Okay, so the ground states of the little string theory are captured by, okay, this is elaborate looking thing. It's called intersection cohomology. The reason why I wrote it in this way, it's actually just square integrable cohomology classes on the modular space of instantons, of SUK instantons, of instanton number n. Okay, that's because in the math literature, in a more rigorous and more concrete way of expressing, cohomology on a space that has some singularities in it, is this. But there is a relationship between the L-squared cohomology and intersection cohomology. And so this here actually captures the ground spectrum of this guy. So, and then this ground spectrum of this guy is equals to modules of SUK. So we end up getting this expression. Okay, so the intersection cohomology of the moduli space of instantons on R4, of SUK instantons on R4, forms a finite submodule over the affine algebra of SUK. Now, this is just a Braverman-Filbert relation. Okay, so this is a math result that has been proven rigorously in 2008, I think, or 7. Okay, so this is in some sense a corroboration or verification of the approach that we've taken so far, the physical approach that we've taken so far. So math corroboration of the physical approach that we've taken so far. So very good, that gives us confidence to carry on. Let's carry on and see what else we can get from this setup that we have been studying. So it also means, therefore, that via the left excited states, okay, which is this one here, right, we would get this new formula here. Okay, so this is something that's new. This is mathematically new, okay, but it's derived from the physics. So what we have here is actually the check cohomology of the sheaf of chiral-Dirham complex, okay, here. And that forms a submodule over the toroidal algebra Okay, that's something new. So this is a novel physical derivation, physically derived generalization of the Braverman-Finkelberg relation. Okay, well, physically you could see the check homology comes in because you're looking at left excited states which have partial derivatives in Z, and that's described by check homology. And then left excited states of the low string theory, you have two loops, and then of the 2-2 sigma model, and then that's how you get the toroidal algebra. Okay, so we can still continue to push this further. So if we use the relevant supersymmetry algebras, one can show the correspondence between the ground states of the little string and the half BPS sector of the M5-brane row volume theory, from which we can compute the half BPS sector partition function to be the following, right? So once you know the ground states of the little string theory, which is described by this affine algebra, we can compute and sum up the states of the affine algebra. Then that will capture a half BPS sector of the M5-brane row volume theory. Okay, and then we end up getting this expression here. Okay, and this here is the character of SUK, okay, in affine algebra that we know pretty well. And it is actually a cousin of a modular form. It transforms almost like a modular form, but not exactly. So we call it the cousin of a modular form, but it does transform as a representation of SL2Z. Okay, and so this is what we get here. This P is just a complex parameter. It's like a fugacity parameter whereby you exponentiate it with the eigenvalues of one of the translations on the worksheet. Okay, so you can see that there is an intrinsic SL2Z symmetry in the M5-brane row volume theory in the BPS, half BPS sector. Okay, that's defined on R5,1. Okay, so, and it emerges, explicitly as gauge theoretic S duality of 4D n equals to 4 superiomials after compactifying on T2. All right, so this is, to me, the most interesting part, right? We are looking at a theory in R5,1 and quantizing it, and understanding its BPS spectrum. And then inside sits a symmetry that we know so well, which manifests itself explicitly once you compactify on T2. Okay, so this is just like the S duality of 4D n equals 4 superiomials. Because 2,0 theory, when you compactify on T2, you get 4D n equals 4 superiomials. Okay, so that's the nice part here. And then we can continue and we study the quarter BPS sector. So we can also show the correspondence between the left excited states of the little string and the quarter BPS sector of the M5-brane row volume theory. Okay, and if you look at the left excited states of the little string, they are given by representations of the toroidal algebra. So we can start summing up the representations of the toroidal algebra, and then from which we, like this, okay, of the quarter BPS states. So it's like a cousin of an automorphic form. So you can see it has 1, 2, and 3 variables here, just like how automorphic forms, the number of variables that you have. And then it transforms almost like an automorphic form, but not really. But it transforms as a representation of SO2 to Z. Okay, so there's an intrinsic SO2 to Z symmetry of the M5-brane row volume theory on R5,1. So that's very interesting. So it emerges as string theoretic T duality of little strings after compactifying on T2. Okay, so again, you see that it emerges as T duality. And one comment that I want to make. So if you look at this one, here we are looking at the half BPS sector of the M5-branes, which are captured by the ground states of the low string. So the low energy, low string states do not have any stringy characteristics. And as a result, when you compactify on T2, you get an SL2Z symmetry of 40 Young males, okay? But in this case here, when you're looking at the left excited states of the low string, you now look at the stringy sort of dynamics of the low string, because you're not looking just at the ground states, right? You're not looking at the lowest energy states, and therefore you're looking at the stringy excitations of the string, and therefore that's why a T duality actually emerges. So in hindsight, the results are consistent, okay? And if you notice that they manifest when we compactify only on T2, that is also because we are looking at the discrete light cone quantization of the low string theory and therefore the M5-brane row volume theory. And in discrete light cone quantization, the R4 must remain uncompactified. So you cannot compactify the 4 directions, and you can at most compactify 2 directions. And that is the reason why our discussions are consistent on T2 and not more than T2. Okay, so if you use a different gauge, we could possibly go beyond this and see more sort of higher rank versions of this, whereby you could compactify down to T6 and then get something like SO66. Okay, so that's pretty much what we will talk about today. So these are the summary of the results. Okay, so let us explain how we got these results. Just give me 10 seconds. That's the great thing about speaking at home. Sorry. Okay, let's explain how we got these results. Okay, just some math, details. Okay, so a loop group LG is the group consisting of maps from the unit circle S1 to a Lie group. Okay, so S1 to the Lie group. So we parameterize S1 by EI theta. So maybe 0 to 2 pi going in a circle. If we impose the base point condition, where at theta equals to 0, it maps to the identity of the group, then we get the base loop group, omega g. Okay, so why we want to study the base loop group is because we want to utilize a theorem by Atiyah that is only valid for the case of the base loop group and not the loop group itself, okay, due to some technical reasons. But physically, it will work out very nicely for us anyway. So one can show that this loop group is just LG mod G. All right, so it is a G equivalent subset of the loop group which is endowed with an LG action itself. Okay, so the point is that the base loop group admits symplectic 2 form, omega. Okay, so very nice. We can study an A model on it. So the complex and symplectic structures of the loop group are compatible, and they conspire to make it an infinite dimensional Kähler manifold. Okay, very nice. So more things on the loop group. So if we let zeta and eta be elements of the loop base loop algebra, then we can write them as follows. Okay, so we can write them as follows. So what's different from a typical Lie algebra is that you have a theta parameter here because you have a loop. Okay, and then you can expand it in this form. So these are the regular Lie algebra generators of the group. Okay, which is in some sense you can understand it as being the base of that the LG, whereby you have this S1 loops mapping onto the base, if you will. Okay, so these are the Lie algebra generators here, and then the ends here represent the degrees of freedom of the loops mapping, and there's an infinite degree of freedom of S1 loops that can be mapped into the group G, right? And therefore that is why we have n taking all values of integers, and then theta here just parameterizes where you are on each of the S1 loops. Okay, the angular coordinate on each of the S1 loops. Okay, the base point condition just means this, which translates to this, which we use in our calculation later on, and it simplifies very nicely. It's very good. So the metric of the loop group, base loop group is this. So what's different from the usual metric of a manifold that's not a loop manifold is that now we have, you see, if you look at the indices here, right, these are like the coordinates of the target space, or that will be the target space of the sigma model. You have the A coordinates, which are representing directions on the group itself, and then you have the M, which represents directions in the space of the loops. Okay, so that's why there are two indices here, and then the metric is given by this thing. This is the Killing metric for the Lie algebra. And if we write this out, this part here, we write this out as this, then we have this loop algebra. Okay, it looks pretty much like the usual Lie algebra, except that you have an extra index for the loop. Okay, the space of loops. Okay, so let's talk about the sigma model now. So the action of the n equals to 2 supersymmetric sigma model CP1 with omega loop group SUK is this. Okay, so it's pretty much the same as the usual sigma model that we have, just that the indices are now, they take, instead of I and J bar, it's this form. Okay, there are two indices now. Okay, so there are two indices now. These are worldsheet coordinates, Z and Z bar, but these are target space indices here. Okay, so they take this form. It's exactly, if you look at the Lagrangian, it looks exactly the same as the usual 2-2 sigma model, just that the target space index is now A and M. Okay, and so we have written, and because if you remember, the n's and the m's take all values of integers, even negative ones, so we have conveniently reparameterized things that look like this with negative as a bar and all that. Okay, so this is just some details that we rewrite it in a way that's very close to the original form, that is not whose target space doesn't contain a loop. Okay, and this is the usual covariant derivative. Okay, so here are the scalars, here are the spinors, Riemann curvature 4 tensor. This is the gamma matrix, the Christoffel connection. Yeah, not gamma matrix, sorry, Christoffel connection of the target space. Okay, so that's looks so familiar for people who work on this. So this is something that's pretty familiar. And so now we want to twist the model. Okay, so we want to twist the model. So we want to do one of the two possible twists. So in 2 dimensions, in 2-2 sigma models, in 2-2 supersymmetry, you have 2 U1 currents, and you could twist using either one or the other U1 current. So if you use one of them, one particular one, I can't remember if it's the vector, it's called vector or the axial one. I think it's the vector one, I think. And you shift the spin of the fields by the U1R charge, then you get an A model twist. Okay, an A twist, all right? And the A twist is the one that is relevant for us, because ultimately we want to associate our A model with our sigma model, or twisted sigma model, with maps from CP1 into the loop group. And that can only happen if you do an A twist. Okay, if it's a B twist, you don't get that, right? So essentially, twisting just means, you know, you diagonally embed the Lorentz group with the U1R group, and in 2 dimensions, it simply is just shifting the spins of the fields by their respective U1R charges. And if you notice in this 2-2 sigma model, the only fields that have a U1R charge are the fermions. Okay, so it means that the bosons, the scalars here, don't get shifted by anything because the U1R charge is 0, and the fermions have different U1R charge, +1, -1, and so depending on the R charge, they would be the spins would shift, and they would either become 0-1 forms on the worksheet or scalars on the worksheet. Okay, so this is what we see here. So this is a 1-0 form on the worksheet.
May I ask?
Yes, sure.
So this sum m and n runs for all integers or positive integers?
Right. So after we do this reparameterization, then it runs for positive integers after this one.
How about 0? N equal to 0.
Yeah, n equals to 0, it will become like the usual sigma model on the group G only.
Then it's not complex?
It's complex still. I mean, the Lie group, Lie manifold of SUK.
Sorry. SUK is not complex manifold. Sorry, I'm confused. Maybe based?
Yes, base. That's right, base.
That makes a difference?
Yeah, that makes a difference. That's right. That makes a difference. Because we need a base condition for this to work. Yes.
Okay. All right. Okay, thank you.
Okay, yeah.
So you don't have to have n equal to 0, or you still have?
We are not studying the n equals to 0 case. Yeah, we are not. Yeah. So nowhere are we studying the n equals to 0 case. I mean, we do study. Yes.
By the base condition, n equal to 0 is written in terms of the others, so n can be positive.
Yes, that's right.
Okay. Thank you very much.
Yes. Yeah. Okay. Yeah. Okay. Let's continue. Okay, so this one is the usual twisting. So you either get 0-1 forms or 1-0 forms or scalars on the worksheet, and then you can rewrite it into a form that is very familiar with the topological A twist model that you see here. Okay, and then here is the worksheet instanton term, all right, where you have a map from CP1 to this base loop group of integer degree n. Okay, so we can write it as this. Now let's study the properties of this guy. Okay, so like the fermion fields, there are 2 nilpotent scalar supercharges when you twist it in the A sets. Okay, there's a Q plus bar and a Q minus, and the Fourier transformations are being preserved on a worksheet of any genes because they are scalars, right? So in particular, if you look at the Q plus bar supersymmetry transformations, then they take this form. Okay, where this is a scalar plus 1 in parameter. All right. Now the action, so this is the part which is where we are doing a half twist. So the action 11, okay, the 11 action here, this specific action here, can be cast into the following form. Okay, it requires some calculation, but it can be cast into the following form. It can be cast into a Q plus bar exact form, okay, whereby there is this thing called the gauge formula. There's some fields inside here which are multiplied by T inverse, okay, plus some terms here. Now the terms here are metric independent terms, so you can scale the metric of the target space and it doesn't matter. Okay, so this T here is actually the metric scale of the target space. So this is and this here doesn't depend on the target space metric. It just depends on the complex structure. Okay, and then this last term here comes from the pullback of the omega, the symplectic form. Okay, and the T also appears here because this is a metric scale T, and then you pull back the symplectic form. The omega itself is constructed from the metric of the target space. Okay, so then the T also appears here. All right, so we can write it into this form. It takes some work, but I think but after, you know, we can write it into this form. So now let's analyze this action. So although the stress tensor, okay, the holomorphic one with ZZ coordinates, which means you take a variation of S with respect to GZZ, is Q plus close. We can show this. It is not generically not Q plus exact. So it's not Q plus exact. Okay. So this is unlike the case of the topological A model, whereby it is basically Q exact. The stress tensor is Q exact for all components. Okay, and that's because it's Q exact with respect to different combination of supercharge. You in the usual A model, you're actually, you know, a sum of this and this as the scalar supercharge. But now we are looking at just one and not two of them, not the sum of them. Okay, so and when that is the case, this TZZ itself is not Q exact. Okay, only the holomorphic, anti-holomorphic component of the stress tensor is Q exact. Okay, so what this means is the following. So if you look at the correlation functions of Q close but not exact, then the reason why we don't consider exact, we consider observables which are not, we don't consider exact Q exact observables is because the expectation value is 0 because they are Q exact. So if you look at just the Q close observables O here, okay, they won't be completely independent of arbitrary deformations of the worldsheet metric G. So in other words, you know, the observables they are not coordinate independent. So they depend on Z. Okay, and how you could see this is the following. So if you look at TZZ bar, if you look at the modes of this guy, it gives you L0 bar. Okay, L0 bar counts for you, you know, the conformal dimension in terms of the Z bar, and that will be 0. But this guy here, which will count for you L0, okay, that is not 0. Okay, because it's not Q exact. All right, so in the topological case, both are Q exact. So then if you add this on an operator, an observable, to check whether it has any Z dependence, it's none. And then you use this to check on the operator observable if there's any Z bar dependence, there's also none, because both are Q exact. Q exact is, you know, equivalent to 0. Okay, so you act on it, it's 0, right? So in this case of a quasi-topological sigma model, A model, the operator observables contain a Z dependence. Okay, and therefore they are not completely independent of arbitrary deformations of the worldsheet.
So I have a question. So
yes.
Yeah, so the ATIA result you were referring to at the introduction. So it says that as far as instantons are concerned, the TCP1 model with the loop group is the same as the instantons of the 4D YAML series.
That's right. That's right.
I guess you are doing the supersymmetric version of setup, but then can you say that what you have been describing here can be equivalently described as far as the instantons concerned, but by starting this 4D n equal 1 and doing the holomorphic topological holomorphic twist, like people call it twist. Do you think that's another description I can think of? Are these two equivalent?
Okay, so the ATIA math result is just, you know, specifically talking about the moduli space of instantons on R4 and moduli space of holomorphic maps into loop group. Okay, so I think in any physical theory which has these ingredients, I think you can employ this math identity. But I think about what you're saying is you want a physical derivation of the RTR result. Is that what you're saying?
Well, let's see. At least it contains the Hody, Yang-Mills as a bosonic. In other words, we can try to supersymmetrize the,
Okay. I see. I supersymmetrize the result by RTR. Is that what you're saying? Something like that.
That's right. Well, as I said, his result is specific about the instanton sector.
Yes.
But you can try to, promote it to statement about physical series and try to supersymmetrize and do the same twist on the both sides, and then try to see whether they give the same content. So so that gives possibly another way of looking at what you're doing, and I wonder whether these are that another viewpoint is really applicable to your problem.
So maybe we can think about that a little bit more. Seems like something is going on there, because you're right, for n equals to 1 the twist is holomorphic, and then you get all these affine currents coming out also from there. Sadov, I think Johansson worked on this many years ago about that. So we can think about it. Maybe we can discuss after the talk. It's possibly. Yes. Okay. All right. Let me continue. Okay. So if you look at the correlation function of observables O, okay, it has the form this, right? So if you put O inside, then you can write it as the path integral very explicitly. Okay, notice that this part here, right? If you differentiate respect to t, okay, it's actually 0. Okay, why? So there's a t dependence here. Okay, and then you bring it down. Okay, it's going to be a q exact term. Okay, there's no t dependence here because it's independent of the metric. Okay, and then because these guys here are also q close, we can just bring it all in, into a q close operator like this. Okay, q exact operator. Sorry. Okay, and then supersymmetry, that expectation value is 0. So you can see that this part here is independent of t, and so we can compute this correlation function of observables with any convenient value of t. Okay, but we can still keep the original value of t on the outside the same. Okay, so this is the part which keeps the worldsheet instanton number, and that is the premise of quantum cohomology, and that you have this term here. Okay, so in the usual topological A model. Okay, so this is the nice thing. So we can compute this guy here, okay, for any value of t. Now, if we take t to 0 limit, okay, then you can see that the path integral over Fn, right, the one in brackets, localizes to q plus fixed points. Okay, so you can see that, right, this guy here, this path integral here. Okay, if you take t to be very small, then 1 over t becomes very big. And so, because of this minus sign, it will localize to the minimum of this guy. You can extract the t inverse out as a factor. Okay, so it localizes onto q plus fixed points. Okay, here. And from 12, okay, what configurations are this? From 12, you can see that the q plus fixed points are just configurations whereby you set these variations to 0. So, okay, so you set this to 0, chi is 0, so chi is 0 here, and that's fine. And then you see that, okay, it becomes holomorphic maps. All right, so this here must be 0. Okay, so del z bar of phi. Phi itself is the map from sigma model worldsheet onto the target space, and del z bar equals to 0 just means that the map is holomorphic. Okay, so all right, so then these are holomorphic maps from CP1 to the base of the group. So the Q plus cohomology of the model.
I'm sorry to interrupt.
Yes.
Sorry, this is my fault.
Yes.
What was T and what was N? Sorry.
So,
T and N. I just couldn't.
T and N. You mean
What
T?
are T and what is N?
Okay. Oh, sorry. N. Okay. N is the degree of the map. The instanton, the worldsheet instanton, the degree of the map here. Here.
Okay. What is T?
T is a scale on the target space metric. Matrix target space metric. T is scale on target space metric.
So the target space is the base loop space.
That's right. Correct.
And you wrote down some metric, and there was T in front.
Yes, that's right. Yes, we can. Yes, that's right. Yeah.
Sorry. Thank you very much.
Yes, yes. Okay. Yeah. Okay. So yeah. Okay. So we have this holomorphic maps here. Okay, so the Q-Pascal homology of the model has ground and left excited states, as I mentioned, because you can have operator observables that also have partial derivative in Z. Okay, because it has a Z dependence, right? So they have the ground states which are no partial derivatives, and therefore they match with the topological A model. Okay, and they are left excited states. So the operator observables O have holomorphic dimension 0 and positive, okay? And these are check homology classes of the sheaf of Caro-Durham complex, okay? But now on the modular space of holomorphic maps from CP1 into the loop group, okay? Simply because, yes.
Sorry to interrupt one second.
Yes.
You said chiral dimensions. So the stress tensor, what is the algebra of stress tensor?
The algebra of the
Cuba plus homology?
Right. So you see the holomorphic stress tensor is Q close but not Q exact. Which therefore means which therefore means that if it acts on an operator, right, the L naught eigenvalue is not 0.
Right. So does it form Virasoro algebra?
Yes, it still does form Virasoro algebra. The
what
holomorphic
is the central charge?
The central charge is it depends. There is a central charge. Yeah.
What is?
What is the central charge?
The value of the central charge.
The value of the central charge. It depends. It depends on some geometry of the target space. I don't recall. It's in the paper, I think. We can discuss later on by looking at the paper.
This is just a base loop space. For that, what is that? It's some finite value, or
yeah. That's right. It's still some finite value. The central charge doesn't blow up.
Even though it's infinite dimensional space.
Yeah, it doesn't blow up. I don't think it blows up. Yeah.
Some k dependent number.
Yes, that's right. That's right. It does depend on the geometry. So yeah.
Okay, thank you.
Okay. So then we have the holomorphic dimension 0 and positive. Okay. And these are given by check homology classes of the sheaf of CDR. Okay, on this guy now. Okay, and that's because our this correlation function here localizes to holomorphic maps. So you have an integral, okay, over the space of maps, and therefore these observables here, in the topological A model, become differential forms on the modular space of holomorphic maps that gives you Gromov-Witten invariance. But in the half-excited states, you get something that is, excited version of the Durham complex of the space of maps, and that would be the Caro-Durham complex on the modular space of maps. Okay, so this is the thing. All right, so we are done with the A model. I'm sorry if I'm taking up too much time. How much time do I have left? Okay, yeah. So isometries. Okay, so let's talk about how the toroidal and affine algebras actually appear in the 2+ homology. Okay, so isometries of the target space, okay, are inherited as worldsheet symmetries of the sigma model. Right, this is something quite intuitive, right? So if you look at the base loop group, it is LG mod G. So our sigma model ought to have an L SUK symmetry on the worldsheet. And indeed, we compute the corresponding united currents, okay, the J's, which charges generate a symmetry of the sigma model, right? Because they're united currents, so they generate a symmetry, and it can be shown to obey a current algebra associated with, the loop group of SUK. Okay, so as the J's generate a symmetry, they act to leave the Q homology of operator observables invariant. So it means if you act in the J on an operator observable, it should give you another operator observable that is within the set of the Q+ homology. Okay. Thus, they ought to be Q close, but not Q exact, and are therefore also in the Q homology. And one can verify this. Very nice. So now let us compute the OPEs, okay, of this operator here, the J operator. So we can conveniently compute the correlation functions of the J operators anti-ZZ via a large T limit. So remember earlier on we saw, okay, that the path integral doesn't depend on T. So we can take the large T limit, okay, to compute things. So as OPEs, okay, the Large limit is just a perturbative, one loop limit, and therefore we can use OPEs, okay. And then you compute that, in some Cauchy instanton sector n, that n data is, kept by the e to the power minus Tn on the outside, okay, for the n instanton sector. So we get this OPE here. Okay, so it looks very close to the usual affine algebra kind of OPE, okay. And then with the T, it has also an OPE here. Okay, so you see like very similar forms of the affine algebra, okay, but this is a toroidal one because you have essentially one extra index here. So in the usual case of affine algebra, you just have the Lie algebra index and then the Z. Okay, this is the current. We haven't expanded out into the Lorentz modes yet. Okay, so this is the current. Okay, then of course we can do a residue, okay, of that OPE to get the commutator. Okay, and then we get this double loop algebra here. Okay, so that's when the other index starts to appear. Okay, so then we get this, and then we get this. So it looks very, very similar to the affine algebra, except that you have an extra index here, which is the N1. Okay, so in the usual affine algebra, you only have one index. Okay, so now we have like two indices here. Okay, so in the holomorphic dimension 0 sector, okay, which means that this operator, which is given by this guy, okay, the rest must act trivially. Okay, in other words, it must be Q-exact. And from 19, we can see, okay, if you put the 0 here, okay, and then you can see that if this operator were to be annihilated by this guy, M must be 0. So we see that M equals to 0. And if you substitute M equals to 0 in this here, okay, then you see that the loop algebra reduces to just the usual, affine algebra. Okay, the double loop just reduces to the loop algebra. Okay, so L goes to just L. All right, and then this looks like the affine algebra. Okay, we have not included the central charges because we are looking at just the first order OPE. There are some corrections that come with higher order contractions of the OPE, which will then give us the central charges. Okay, so this is also the topological sector, since TZZ is now assumed to be Q-exact. So that's the thing about this half-twisted model. You have the ground state sector, which is corresponds to the topological sector that we know so well, but you also have the half-excited ones. Okay, so then we get this. So our aforementioned J's were derived from a classical Lagrangian density, and there will be quantum corrections. Okay, so and then therefore there will be central extensions, and these are ascertained by looking at the higher order contractions in the OPs. Okay, and then eventually when we work this out, then we will get a form that's like this, and this is a toroidal Lie algebra. Okay, we actually get a toroidal Lie algebra, and then in the topological sector we get an affine Lie algebra. Okay, so these are the new things that come from analyzing higher order contractions. Okay, and very nicely again, when you let the M index go to 0, because that's the conformal dimension 0 case, okay, of the L0 operator, and then you see that it just becomes this one here.
Excuse me. So if you replace the group more general ones, and you still get the toroidal Lie algebra and affine Lie algebra?
Yeah, correct. Yeah, up to this point, we haven't, we don't need it to be SUK yet, up to this point. We only study SUK because of we want to study the AD 2,0 theory, the A 2,0. Yes, it should work for other groups, at least physically in this thing.
Yeah, because I'm asking because Bregman-Finkelberg proposal, it involves the Lagrange Lie algebra, affine Lie algebra. How do you see this Lagrange Lie?
So, yeah, so to do that, to get the Braverman-Finkelberg, which I explained before, you must relate it to the 2,0 theory first, the little strings one, okay? And in that case, there is only an ADE sort of 2,0 theory. And so then to get the Braverman-Finkelberg relation for non-simpliles, then we cannot use this approach because this approach requires us to make reference to the AD 2,0 theory.
I see.
Yeah. So that's the thing. It works for simpliles only. Okay. To make connection with Braverman-Finkelberg is only for ADE.
Okay. Thank you.
Yeah. Okay. So okay, so we have this so these two things here: toroidal Lie algebra for the half excited one, and then the affine Lie algebra for the topological one. Okay, so then we can use the usual, usual thing in quantum mechanics, quantum field theory. We have ground state, which is supersymmetric, so Q plus close, and then we act on the generators of SUK, right, on this guy. Then we form states. So these states, they span a module of this toroidal algebra. Okay, these states have non-zero holomorphic dimension, as we already saw earlier from 90. Okay, from here. Okay, and then they can be shown to be elements of the Q plus cohomology. So again, you can show that these states are Q plus close, but not Q plus exact. And so via state operator correspondence, okay, we can do the following. So the modules here, which are representations of this toroidal algebra, which are given by these states, we can identify them with the check cohomology classes of this sheaf, of Caudry-Rem on this thing. Okay, so that is the key point here, right? So this non-holomorphic, non-zero holomorphic dimension states, correspond to non-holomorphic dimension operators, and non-holomorphic dimension operators correspond to check homology classes of the sheaf of CDR. Okay, and then in the topological sector, we can also generate these states here, and topological sector is when this M index is 0. And then these actually span a module for the affine Lie algebra, okay, of level C1. These have, zero holomorphic dimension, as we mentioned earlier on. And then through state operator correspondence, it corresponds to zero holomorphic dimension of the CDR complex, and this is just a usual DRAM complex. So we have L-squared cohomology on the space of maps, even identified with the affine algebra of SUK. Okay. Right. Okay, so we are not discussing the Braverman-Finkelberg yet, because this looks like Braverman-Finkelberg. Okay, looks like, but this space here is different. Okay, but Atiyah, had a theorem which identifies this space with the instanton ones. That's how we are able to make this correspondence. Okay, so now, little string theories. Okay, let's just talk about the 6D 2,0 little string theory, the A type. Okay, so little string theories exist in 6D space-time. Okay, they are literally little strings, and they're reduced to interacting local QFTs when the string length goes to 0. Okay, so when the string length goes to 0, you're at the point particle limits of the string theory, and it becomes a quantum field theory, right? The 6D A type 2,0 little string theory, in particular, reduces to the 6D A-type n equals to 2,0 superconformal field theory that we know so well. That has given us so many results, geometric Langlands, in 4 dimensions when you come back to 5 and T2, and a lot more things, all right, that we have found, AGT and all that. So it's a really rich theory, and it comes from the point particle limit of this little string theory. So this 2,0 theory has no known classical action, but that doesn't mean we can't study them. Okay, if we look at the canonical quantization approach to quantum mechanics, we can look at the symmetries of the algebra and still ascertain the states from the symmetry algebra, right? It's a very rich theory, so the little string theory must be at least just as rich. Okay, there are probably a lot of mathematical secrets that are hiding inside here, and we are unraveling some of them today. Okay, so that is the point of this work, right? We are going beyond just the ADE superconformal field theory, looking at the little string theory. Okay. So it is also, this little string theory, it is also the world volume theory of a stack of NS5-branes in type 2A string theory, okay, whereby the fundamental strings of type 2A theory, they reside within the branes. So it's like a stack of NS5-branes, and their little strings, they are strings inside, okay, and the coupling for these strings goes to 0. So they decouple from the degrees of freedom, including gravity, okay, in the bulk, all right. And when the string length is not 0, you can actually see the strings, okay? And these are the little strings that live inside the NS5-brane. Okay. So there's a way to understand these little string theories from work back in the late 90s. A lot of people have tried very hard to understand it. And one of the ways is to do this thing called the discrete light cone quantization, or DLCQ method of the little string theory to ascertain its spectrum, okay? Where little string, the NS5 world volume is R5,1. So it can be shown that if you use the discrete light cone gauge, you can describe the little string spectrum in terms of a 2D n equals to 4 sigma model on a cylinder S1 cross R with target the modular space of SQK instantons of instanton number n on R4. Okay, so bear in mind that this is not the sigma model that we were talking about earlier. The sigma model that we were talking about earlier was a 2-2 sigma model on target space, the base loop group. Okay, it's a different thing. So do not be confused that our 2D sigma model, the 2-2 one, is an auxiliary physical theory that we are going to use to allow us to understand this a bit better. Okay, so but in the case of the Lycombe quantization or little string theory, it is actually a 4-4 sigma model, okay, on a cylinder with target space, the modular space of SQK and instantons on R4. Okay, so this has been summarized in the review by Digraph of work over several years, where many people have worked on it in the late 90s. And K here is the number of branes, okay, and therefore that also tells you sort of the gauge group, the rank of the gauge group of the NS5 brane. Okay, so K is number of branes, and N, which is this in this case here, the modular space of n instantons, they are like discrete momentum along the S1 of this 2D sigma model. Okay, so the ground states of the little string theory, okay, in the discrete Lycombe quantization are given by sigma model states annihilated by all the superchargers. Okay, this has been established. So therefore, they correspond to harmonic forms and thus L-squared homology forms of this guy, the modular space of SQK instantons. Okay. Now, the left excited states of the little string theory are given by sigma model states annihilated by 4 chiral superchargers of this 4-4 model. Okay, so they correspond, therefore, to check cohomology classes of the sheaf of chiral DRAM on this guy. So this statement that we have made here, the arguments are parallel to what we said earlier on about the 2-2 model. Okay, so if you look at the Q plus, so if you look at the Q plus bar, the 4 chiral superchargers of the 4-4 model, then you will end up with the same conclusion about this thing here. Okay, so it's parallel. All right, so we have this. Okay. So according to Atiyah, there's a very nice identification of these two spaces. Okay, the space of n instantons on R4 is the same of the modular space of n instantons on R4 is identified with the modular space of holomorphic maps, degree n from CP1 into the base group. Okay, so in turn, this means we can have the following identification. Okay, so sorry. So the L-squared cohomology that we had on this guy can be identified with the L-squared cohomology that we have on this guy. Okay, and likewise the check cohomology we have on this guy, we can identify the check cohomology that we have on this guy. Okay, very nice. Thus, okay, now that we have this identification, that's the crucial part. So if you look from 28, so 28 we use this one for the cohomology, the identification. Okay, and 26 we saw this, right? 26 we saw this for the ground states. Okay, we had this thing here. So we just replace this guy with the identification that we saw early on that has to do with instantons on R4. Okay, and then we can come to this conclusion. All right, so the ground states of 6D AK - 1, which are given by instantons on R4, right, will be given by modules of SUK. So likewise, from 29, which identifies the check homology on the space of instantons, which then gives us the left excited states of the little string theory. Okay, and 24, okay, here. So, all right, and this guy is identification here with toroidal algebras, then we can make the following conclusion. Left excited spectrum of 6D, little string theory is given by modules of SUK toroidal algebra. Okay. Then very nicely, we can just easily get this Braverman-Finkelberg relation in reference 2. Okay, so from 30 here, looking at this ground spectrum one, this one here. Okay, so the ground spectrum, as we saw, given by cohomology classes on the space of instantons on R4. Okay, and then we will have this. So this is Braverman-Finkelberg. So up to this point, this, at least for us, it serves as a mathematical verification of the physical approach that we have taken so far. And of course, the usage of Atiyah's theorem in our approach to studying the physical model. Okay, so this is very nice. We are very happy when we got this. IH, because there is a identification of L-squared classes with intersection cohomology. This is given by Gorski in reference 5. So for the math people, you're wondering how we jump from L-squared to IH. This is the reason. hang on, I have a, okay, sorry.
Excuse me. How do you understand the cohomological degree in representation terms? So this was, I think, one of the Brebman-Finkelberg proposal.
Yeah. Sorry.
How do you understand the cohomological degree?
The cohomological degree. Okay. Like you mean for this one inside here?
Yes.
How you map the thing?
Mm-hmm.
How you map the thing inside? Yeah. So the cohomological the in terms of the degree of the forms, like what's the degree of the form? It's that inside there is okay. So the degree of the form is given by the R charge of the operator in the sigma model. Okay, in this sigma model, is given by the R charge of the operator. Because if you
I'm asking how do you understand this the Brzezinski constant filtration in the right hand side?
No. We are just using the mathematical result. So to write it in a form that looks recognizable by mathematicians. That's the reason.
But still, I mean, is this isomorphism of graded vector space or just a vector space?
It's a vector space. Yes. So we have L squared. Okay, in the physics.
So you can consider the cohomological degree also in this.
Yes. So this was explained in Vygotsky in reference 5. So that's why we can rewrite as IH.
So then you can analyze the cohomological degree in physical way.
Oh yes, you can also. The cohomological degree in physical way is given by the R charge of the operator, and the R charge of the operator corresponds here to a grading inside the affine. So there is also a match.
So you mean this Brzezinski constant filtration can be?
Yes, it's hiding inside the thing. Yes, it's hiding inside. Yeah.
Okay, thank you.
Yeah. So and then so this is Bellman-Finkelberg, and then if you look at 31, that gives us a generalization, right? So if generalization, so the left excited spectrum, okay, that's given by the check homology on a space of instantons. And then that's related to modules of toroidal. So we actually get a generalization of Bellman-Finkelberg. But now not in terms of regular cohomology, but check homology of Cairo-Durand complex. Okay, so this is something new. All right, so maybe this is something which our math friends can try to verify or think about. Okay, that's our sort of contribution from physicists, to mathematicians, right? Okay, so finally, yes.
This discussion, you decouple the stringy modes, and then what is the corresponding operation?
If you decouple the so the decoupled stringy modes is this guy here. You get this answer.
Oh, 32 versus 33.
Yes, correct. So yes, that's right. So the stringy ones, you get this.
I see. Okay. So
yeah, so that's why we can get this even from 2,0, the QFT. This was first physically derived from 2,0 QFT.
I see.
Yeah, so that was the work I did when I was at the IIS in 2008, where I did the 5-branes and the geometric Lagrange duality. I was looking at the 2,0 only. 2,0 quantum field theory, not the little string, no stringy modes yet. So we get this by just looking at the QFT version of 2,0. We get this once we consider the excited states of the little string. So you can see the stringy excitations. Yeah, so at higher energy, then we get this basically.
Okay, thank you.
Yeah, so if you will, this is a stringy generalization of the, of this result actually. So in that sense, this is like quantum mathematics. This is like string mathematics, if you will. Yeah. Okay. Okay. So the M5-brane world volume theory. Okay. So we have talked about Bellman-Finkelberg, its generalizations, little string theory, and how we were able to use the auxiliary sigma model on base 2 group to get the spectrum for the little string theory. Okay. Let's now discuss how what we have done earlier on can allow us to know about the M5-brane. Okay. And if you think about it, it's not really surprising because the NS5 brane is related to the M5 brane, and so we're studying little strings in NS5 brane. So that should be able to tell us something about M5 brane. Okay, so it's a bit wordy here. I think I've sort of overshot my time. So let's just I'll just summarize what I've said here simply as if we want to study the M5 brane world volume theory, it suffices for us to just study the little string theory on the NS5 brane. Okay, for the very obvious reason that the NS5 brane comes from the M5 brane anyway in type 2a, right? And the little strings that are residing in the NS5 brane come from the M2 branes that are wrapping the 11th dimension anyway. So they originate from the M5 branes, the M branes in M theory. So we can just study them. Okay. So essentially, the low energy DLCQ discrete Lagrange quantization of the world volume theory of KNS5 branes, KM5 branes can also be understood via little string theory. Okay, which is described by the 4-4 sigma model on the space of instant points. Okay, on R4. Okay, so how do we sort of study the BPS? What we want to do is study the BPS sector of the M5 brane world volume theory. Okay, so if you look at the M5 brane world volume theory, it has 2,0 supersymmetry algebra. All right, because it's half BPS, so it preserves half of the 32 supersymmetries in M5 in M theory, and therefore you have 16 supersymmetries which are chiral. Okay, and so the algebra looks like this. So in DLCQ, only 4 directions are unrestrained. Therefore, you have this Lorentz index that goes from 1 to 4. Okay, and then you have the chiral and anti-chiral index that goes 1, 2. So the H and the P here are just generators of translations in the other 2 directions, which are not fixed. Okay, so which are fixed, sorry. Okay, so this is the algebra for 2,0 theory in discrete Lagrange quantization. Okay, you can see that there are 16 supercharges indeed. Supercharges of this type, this counts from 1 to 4 and this counts from 1 to 2. So you have 8 of this type and then another 8 of this type. So you have 16 supercharges and they're all chiral. Okay, they don't have a bar in the expression, so they all are left moving. Okay, so if you look at the half BPS sector of the world volume theory, they consist of states which obey the 4 chiral relations and the 4 anti-chiral in not in the space-time sense, but in terms of this index sense. Okay, the R symmetry sense. Okay, so you can see that the BPS states that are half BPS of the world volume theory must be annihilated by these supercharges and also these supercharges. Okay, and you can count here that indeed there are 4 here and there are 4 here. So you can see that they are annihilated by 8, supercharges out of the 16 of the world volume, and therefore half BPS. Okay. So there are in the M5 brane, of course, there are M strings that are living inside. Okay, which we already said are the M2 branes wrapping the 11th circle and then being embedded in the M5 brane world volume itself. And these will descend to NS5 theory in type 2a with little strings inside. Okay, so since the M strings that live on the M5 brane world volume are half BPS objects, okay, so M2 branes are also half BPS object, they will further break half of the supersymmetries of the 16 that live in the M5 brane world volume. So there are only 8 of them. Okay, so they will only preserve 8 of the 16 supersymmetries on the worksheet. These M strings will only preserve only 8 of the supersymmetries. Now, if you look at the 8 preserved supercharges on each M and therefore little string worksheet in the lower type 2a theory, they obey this algebra. Okay, so you can see from this algebra, there are indeed 8 supercharges. Okay, because this takes up 1 and 2 index. This is 1 and 2 index. So there are 4 of this kind and there are 4 of this kind. So indeed, there are 8 supercharges. But now the chirality is different. So there are supercharges that don't have a bar and the supercharges that have a bar, and this is associated with the left and right moving Hamiltonians on the worksheet. So we end up getting a 4-4 model. So we actually, the M string itself, it actually has, on the worksheet itself, it has 4, 4 supersymmetry. Okay, and it's given by this algebra here. And these supercharges here actually come from the ambient 16-dimensional supercharges of the world volume theory. They are being preserved, when they hit the M string. Okay, the rest are spontaneously broken by a super Higgs mechanism, which was described by Polchinski very nicely in the textbook, right? Okay, so And you can see that the 8 preserved world sheet superchargers, as I mentioned, they are 4 chiral and 4 anti-chiral, okay, and they actually correspond to the world volume superchargers, whereby AB12 is actually AB34, okay. So hence the half BPS sector spanned by states obeying the 4 chiral and anti-chiral relations here, 35 and 36, is also spanned by states annihilated by the 4 left moving and 4 right moving superchargers on the worksheet. So essentially, you know, this M string, okay, itself has 4-4 supersymmetry, okay, and the half BPS sector of the world volume theory are the same as the states that are being annihilated by all the superchargers on the M string itself, okay. So from the supersymmetry algebra 37, we find that these states are necessarily ground states, okay, right? So they're annihilated by all these guys, so annihilated by this and this, and therefore they're actually, the Hamiltonian is this, and then it's also annihilated by the Hamiltonian. So they're actually ground states. So what we can say is that the low energy half BPS sector of the M5-brane theory is captured by ground states of the little string theory. Okay, good. And therefore, according to 30, okay, we saw the ground states of little string theory, okay, whereby we were able to derive this using the auxiliary sigma model that we used earlier on of 2,2, right? The modules here, okay. The partition function of half BPS sector of this M5-brane ought to be given by summing the representations of SUK, affine, okay. So in particular, we compute it to be this guy here. Okay, so this is the usual character that we have of affine algebra. Okay, in some complex parameter P, which is like a fugacity parameter, which you exponentiate with one of the translation operators on the worksheet. And alpha prime hats is dominant highest affine rates, okay, of the character. And so if you look at this expression here, okay, it's like it's almost like a modular form. It transforms almost like a modular form. It's like a cousin of a modular form, but it does transform as a representation of SL2Z, as we mentioned right at the beginning of talk. So we see there's an intrinsic SL2Z symmetry in the M5-brane volume theory on R5,1. It's hiding somewhere inside. Okay, there's a symmetry that even in the BPS sector, right? And to see it emerge explicitly, you know, it emerges as gauge theoretic S duality of 4D and 4 after you compactify on T2. So that's how it actually emerges explicitly, you know, in a lower dimensional theory. So same thing we can do for quarter BPS. So quarter BPS sector, instead of being annihilated by the 2 conditions, is only annihilated by one of the conditions. Okay, so this is the condition for quarter BPS. All right, so you can see that there are 4 superchargers that annihilate the BPS states. Okay, hence the quarter BPS sector is also spanned by states annihilated by just the 4 right moving superchargers on the worksheet of the M string or the little string. Okay, so and then you can see from the algebra of the little string theory, the M string and little string theory, that these are the states which have, you know, 0 conformal anti-holomorphic conformal dimension, but non-zero holomorphic conformal dimension, right? So thus the low energy quarter BPS sector of the M5-brane theory is captured by the left excited states of the little string theory. And again, same thing from the left excited states of this little string theory, we relate it to modules of this guy, okay, the toroidal algebra. So it means that the partition function of the quarter BPS sector ought to be given by summing representations of the toroidal algebra. So in particular, we can compute it, okay, and then we end up getting something like this. Okay, so again, Q is another complex parameter which now is being exponentiated by the other translation operator on the worksheet. Okay, and R here is related to Q by some expression. This is the Dedekind eta function. This is the usual character. So you can see it's almost like an automorphic form. It has the same number of variables Q, P, and R. You know, almost transforms like one, but not really. But it does transform as a representation of SO22Z. So we can see that it's an intrinsic SO22Z symmetry of the M5-brane volume theory on R5,1. Okay, so it's very nice. So and then when you actually compactify, you know, 2 directions on T2, this is exactly T duality of a string theory. So very nice as a correspondence when we consider, you know, the excited states of the little string theory, meaning the stringy degrees of freedom, we actually get T duality, you know, hiding somewhere inside here. And then when we compactify on T2, we actually, you know, explicitly see this T duality symmetry manifest itself. Okay, so that implies many things. I mean, it also implies that if we were to study string theory in, you know, 10 non-compact directions, you know, the T dualities and all the higher symmetries are actually hiding inside. So this is pretty much in line with a lot of work that people have been doing recently on exceptional geometry and those things. I'm not an expert on that. You know, I organized a conference whereby there were people talking about it, but you know, I've yet to fully master that topic. But a lot of symmetries that we see in string theory are actually hidden, you know, inside, you know, the theory already, even before we compactify the directions. So this is another example of what we see here. Very nice. And so the part which, you know, I would claim that there is some connection to number theory would be these forms, you know, that look close to modular and automorphic forms. All right, so there's some kind of counting, and you know, hopefully we could connect, you know, more concretely to more, you know, abstract number theoretic stuff in math in due time. Okay. So let's conclude. I'm sorry I took up so much time. I lucky thing this is like the last talk for now. We have explained how a quasi-topological loop group, base loop group sigma model can be used, okay, to help us, number one, understand the 6D A2,0 little string theory. Can be used to derive and generalize the Braverman-Finkelberg relation, and 3, to understand the M5-brane world volume theory in the BPS sector. Okay. Notably, we find that the chiral spectrum of the little string theory is furnished by representations of a toroidal algebra. So its stringy degrees of freedom can be associated to representations of toroidal algebra. And the BPS spectra, okay, the half and the quarter BPS spectra of M5-brane world volume theory is closely related to modular and automorphic forms. Okay, so consistent with these aforementioned physical results is the geometric Lagrange correspondence for surfaces, which we have derived physically. Okay, the Braverman-Finkelberg relation, and we also got a stringy generalization of that result, which relates the check homology of CDRs on space of instantons with representations or modules of toroidal algebra. Okay, so we see a nice interconnection between string theory, M theory, geometric representation theory in the sense of Braverman-Finkelberg and geometric Lagrange, and also number theory in terms of these forms that we have obtained. Okay, so for future directions, we intend to do the following. We intend to ascertain the full chiral plus anti-chiral spectrum of the 6D little string theory. We expect it to be furnished by representations of a holomorphic plus anti-holomorphic toroidal algebra. Okay, this is just a very vague sort of guess. It might just be different when we work out the details, but more or less physically that seems to be the case because you're looking at the left and the right moving one. So we could gauge the sigma model, the base loop group sigma model, to obtain a derivation and generalization of the AGT correspondence. Okay, so we could try to do that because if you look at the AGT correspondence, the mathematical statement is equivariant cohomology on the moduli space of instantons. And to get an equivariant version of our observables, we just need to gauge the sigma model. Okay, so we get equivariant Q cohomology, right? So, and then if we look at the stringy generalizations of that, then we would expect to get the following generalization of the AGT, which is the equivariant check cohomology of the sheaf of chiral Durand complex on the space of instantons to toroidal W algebras. So that could be a generalization of the AGT, right? So we obviously, you know, at the end of the day, we would wish to be able to understand M theory to as best as we can. So we would like to go beyond the BPS sector of the M5-brane world volume theory, as captured by the full spectrum of the little string theory. So we expect the corresponding world volume partition function to consist of the quarter BPS partition function, okay, with an extra Dedekind eta function in R bar. In other words, we are considering excitations on both sides, everything. Okay, so and that will give us sort of the whole, all the degrees of freedom of the little string itself. Okay, thanks for listening. I hope thanks for your patience. It's been I've overshot quite a bit. Yeah, but thank you very much. Yeah.
Thank you very much. So, other questions? Oh, okay. Abhiram?
Yes.
Thanks for a very nice talk. I was wondering if you studied some of the automorphic properties of these two automorphic forms, and because you mentioned that they're almost modular, does that mean Mach, or what does that mean?
Yeah. All right. Right. Yeah. You could think of it as some kind of Mach, modular form, if you will. Yeah. I mean, Mach modular forms. They also have they transform homoside modular forms, and that's the reason why they are called Mach. You know. So yeah, you could consider them as some kind of Mach modular form. Yeah. So we haven't looked very closely in the math literature to see, what it corresponds to. But yeah, it probably is something like that.
Because if you're given a Mach modular form, you could try to complete it with something called a shadow. I think also what Atish and everyone mentioned about their talks yesterday, also Jeff and Miranda. So the shadow part, I'd be interested in also understanding if it really is Mach and there's a shadow that you can add to it, like integral, and then complete the Mach modular form. Firstly, is it, I mean, first of all, it's holomorphic. The function is holomorphic, so it's already kind of interesting. And what function you get, what this shadow actually would correspond to physically from your theory. I mean, because you say they're almost holomorphic in both these cases. So I'm just very curious as to what, we could talk more about this later because it's,
Sure. Yeah, so that part we haven't really looked as carefully, or rather as in detail. I mean, the computations are careful, though it's foolproof, but yeah, so yeah, we could explore a little bit more on what these forms actually relate to, and is there a sort of a deeper understanding and connection to other things. Yeah, that's something we can explore.
Right. And also in the SO2,2 story of automorphic form, there's usually something very interesting going on over there. Because when people do talk about SO2,2, you can always do like a reduction, get out SO2,1, which gives you Shimura variety. And there's a very nice story of automorphic forms. And,
yeah, I'm not aware of that, but yes, I think definitely there is room to explore much further from where we have completed this paper. Yeah,
we can chat about it later. I'm happy to talk.
Sure. Yeah.
Other questions?
Okay, then is the level of duality natural in your string linearization of this SU and?
Yeah. Okay. Yeah, it is. Okay. The generalization of Braverman-Finkelberg. Okay, but the thing is that it applies for the ADE only. So
I mean, you also N and K exchange.
Oh, sorry, sir. Again, you mean which one?
Level and duality between level and rank, and K and N in the SUN level K.
Yeah. Correct. Yes. So that exchange is still there. That exchange is still there. Yes. Yeah. No. That's level rank duality, right? No. In the Braverman-Finkelberg, there is no level rank duality. The expression doesn't have a level rank duality.
Oh, okay, it doesn't work. I see.
No. Yeah.
Yeah, if you connect with my result, then natural level rank duality shows up.
Okay.
So I constructed the representation of the affine.
Right. Yeah, in your case, yes. In your case,
I checked the Braverman-Finkelberg proposal using my old result.
Yes.
Together with Braverman.
Yes. Yeah. So of course the very first appearance of this connection between instantons and affine algebra came in Hiraku's work, of course, and that there was a level rank duality there.
Yeah. I was asking because in Hiraku's case, people try to explain it by embedding into string Dio and then top knot and then take Dio, etc. And then level rank duality.
Yeah, right. So yeah, that's right. So in Hiraku's case, because the group on the other side, it's the rank of the group on that side is the instanton number on one side. So it's a quite a different group basically. In the Braverman-Finkelberg, if it's for ADE, it's the same group. At least the Lie algebra is the same. Okay. So and then if it's a non-simply laced generalization of that, then it's A to the Langlands dual of A. So there is no level rank duality, but you can check that their results are correct from level rank duality in Hiraku's work by using another level rank duality. Yeah, correct. Am I right, Hiraku? Right?
Yes. But my argument works only for type A.
Okay. So using the top knot one, I think in that original paper that I wrote in 2008 on two-dimensional duality, I was able to get the A to A, the same one, SUK to the SUK from physics. Yeah, but I wasn't able to get the directly. Wasn't able to get what Hiraku wrote, which was SUK instantons with n to becoming SUN with level k. So I wasn't able to get that. Yeah.
Okay, other questions? I have a question. Maybe once again, this is my fault. I couldn't follow the step of deriving this L2 cohomology of space of holomorphic maps. Is a module of affine or toroidal algebra. Could you show that again? Sorry.
Okay, sure.
Perhaps I just
No, not at all. Yes. Okay. Okay. This one, right?
Right. How do you get?
Okay. So this one here is still about the sigma model on the base loop group. Okay. Okay. So and then these guys here have conformal dimension, holomorphic conformal dimension non-zero.
So this is, you're talking about the space of states on what? On a circle?
So this is the space of quantum states of the sigma model.
Yes. So on a circle. Say.
On the CP1.
What do you mean by state on a CP1? You're talking about two-dimensional quantum field theory?
That's right.
The state should be associated with a one-dimensional space, which is a circle or a segment, maybe circle.
Yes, circle. That's right. So you can think of the CP1 as, you know, a circle over an interval that collapses at the two ends.
Okay, and then so why it is labeled by n? N is associated with a degree, which is
yes. So this n guy here. Okay,
no, not that n. Sorry, capital N.
This here is the degree of the map.
Why that can appear on state? Which no idea about this two-dimensional surface.
Yes. Okay, there is a winding number. So the degree of the map of the worldsheet onto the target space is given by is related to the winding number.
What is pi1 of the target space?
The pi1 of the target space is, the target space that we have is the base loop group.
Is it not simply connected?
I mean, there would be two cycles in it.
No one cycle. Is there one cycle? I'm talking about one cycle. You're talking about one cycle, right?
No, we are talking about the winding number, which is related to the wrapping of the worldsheet on
which
the
is
two cycle,
right? Which is S1. So you need a one cycle, no?
No. We are looking at it as the full manifold of S1 to G, the full manifold.
Okay. Okay. Oh, I see. So this is the winding number. And then I see. Okay. Because it's a loop space.
So essentially, there are two loops. The worldsheet has a loop, the space has a loop.
I see.
Yes, correct.
N means the loop in that space.
Yes, that's right.
No, it's a combination. I see. Oh, okay.
Yeah, it's a combination, I guess. Correct.
Right. That's right. I see.
Yeah. So it's very nice. It all fits nicely.
Okay.
Right. Okay.
And one more. Sorry, one more question.
Sure.
C1 and C2. What is
yes.
it? How do you compute and what are they?
Yeah. So we take the higher. Okay. So we take the higher contractions. Okay, and then we use some consistency conditions to determine what they are. So actually, at this point, to be very honest, okay, we are just having a very, we just made a very good guess of those numbers. We couldn't explicitly compute it, the actual numbers themselves. We know they ought to take this form with some constant here after we do the higher contractions, like this part here. Okay, we got this part from the higher contractions, but the C2, we have used a mathematical result by Siegel on some positive energy states. But yeah, I would say that we need to basically study this a bit more carefully. But it will definitely take this form like that.
So the naive OPE computation doesn't give you the right answer?
Because it ultimately involves some geometry of the target space. Okay, and then that is a bit difficult to compute explicitly. Yeah, but then the accompanying terms here that you can see from the OPE. Yeah, the delta functions and all that you can see. Yeah.
But it's difficult. I see.
It's difficult. It's difficult.
For the case of level thinkable, C1 is just 1. So this is level 1 representation. Is it difficult to derive directly?
Yeah, because the problem is that in the physical calculation, if you have 1 here, like, it's multiplied by some other factors that you can force it to be 1, by some physical argument or rescaling the fields, but it's not so not so easy to get 1 basically. Yeah, so that's the thing. So in some sense, the physics computation gives you more degrees of freedom that you can use by rescaling fields and all that, but it also introduces an ambiguity. So that's the problem. Yeah.
Okay.
Yeah.
Okay, thank you. Are there other questions? If not, let's thank the speaker again.